Okay, I'm starting the recording. Don't know whether. Hello, hello. Okay, okay. So voice is coming. Okay, okay. So you are able to see the slides. Anyone? Praveen, can you see the slides? Hello, hello. Okay, okay. You are able to see. So welcome everyone to the week 6 of NPTL TA session Introduction to Mobile Robotics course. I am your TA Suraj Borate. I am PMR PhD scholar from IIT Gandhinagar, and we will start with our first question. So, as you know, our pattern is that we take up questions from previous year assignment so that you can solve the questions of this year's assignment, which are very similar to the previous ones, and we also take up your doubts related to robotics course and anything else. Okay, so let's start with the first question. So this today's lecture is uh, about path planning problems, and so we'll start with question one. Okay, so for a polygonal configuration space consists of edges joining all pairs of vertices that can see each other. Okay, so the above statement is suitable for which planning method, and there are four options. So there is Voronoi diagram method, cell decomposition methods, visibility graph method, and approximate cell decomposition method. Okay, so obviously this is a theory question, but let's try to revise all the algorithms mentioned in the option. Okay, so what was Voronoi diagram method? So Voronoi diagram method was like, suppose you have some obstacles here, right? Then we try to create edges that are equidistant from all the obstacles, right? So we try to create something like this. Okay, so all the paths that are created are equidistant from the obstacle. Okay, so Voronoi diagram method will give us paths which are very safe, which are away from the obstacle, right? Or you can say that it partitions the space, okay, in a such a way that there are cells and each cell has one obstacle, right? And that obstacle is somewhat in the middle of the cell. Okay, so this is Voronoi diagram method. What was cell decomposition method? So the cell decomposition method was it was something like this. So if there are some obstacles, okay, there are actually different type of cell decomposition methods. Okay, so what we do is we join to the from any either from horizontal or the vertical. We join to the uh, vertices like this. Okay, and we create the cells. Now these are the cells, and there is a method where you can just join to the midpoint segments of the cell and create your graph. So there are two methods that you have learned in the course. Sorry, not two methods, but two steps. First step is to create graphs or graph construction, and the second step is to search on the graph, right? So this one graph construction method can be you join to the centroids of the segments and you create one graph and then you apply some graph search. Okay, so that is cell decomposition, and what I will discuss visibility graph was as you can see what is mentioned in the question is the description of visibility graph. So the visibility graph is like suppose you have been given a map, okay, something like that. So what we do is we from every vertex, okay, we try to join the graph to the vertex that is visible to it. Okay, so we will try to join like that. Okay, so from here, what is visible? This is visible, this is visible, and this is. So we create a graph like that. So this is visibility graph. Okay, and the obstacle edges are also part of the graph. Okay, So what will happen? Suppose your start point is here. Okay, so we'll from start point this two are visible. Okay, let me check the color. So there is no. So this is the obstacle. Okay. So from the start point, these two are the edges. Okay. And from the goal point also we join the edges that are like visible. Okay, someone is joining. So let me let in. So Prasha is here. Okay. So for the goal point also we try to join the visible vertices. Yes. Who is asking the question? Yeah.
Sorry, sir. I mistakenly unmuted.
Okay. Okay. Fine. Okay. So what we do is from start we join to the vertices that are visible, and from the vertices we join to other vertices. Those are visible. Now the question is how to find the visible vertices. So there is something called as ray scan method. So that is not covered in the course, but those who are interested in path planning so should read up in it in more detail. So there is this book by Lavale. So I don't know how to pronounce that, but okay. Um so Laval or Leval. So this author has written path planning algorithms book. Okay, path planning algorithms. Algorithms. Okay, so this book you can read, and then there is principles of robot motion. So this book is also very good. Principles of. So today I don't have my pen, so that's why I'm writing with the mouse. Okay, principles of robot motion. So this book is really good book. You should. I really recommend it. This topic is also very interesting, so you'll enjoy reading. How you chose it. Okay, so if you go into this book, then you will also understand the implementations. So those implementation are not that much covered in the course. So the course is mostly introductory. You cannot have every subject in robotics covered in one course, right? So yeah, so the idea is that the polygonal configuration basis consisting of edges joining all pairs of vertices. So we are joining all pairs of vertices. So this is visibility graph method. Okay. Uh, and then there is this approximate cell decomposition method. Okay, so approximate, I don't really recall what was it. So cell decomposition we saw. I think in approximate cell decomposition we used to. Uh, so can anyone recall what was the difference between cell decomposition and approximate cell decomposition? Anyone? Yeah. So what I recall is that. I don't think it was covered, but let's see. So in cell decomposition, what we do is, we there is also way of defining a grid. Okay, a grid on the map. Okay, and then which is one and which is zero that we can define. Okay, so like which one is covered with obstacles and which one is not covered with obstacles that we can define. Okay, so but in approximate, what we do is we can reduce the number of cells by having variable size grid. Okay, so we can have so like final grid near the obstacles and a coarser grid outward. Okay, so this is like approximate cell decomposition method, and there are ways of creating it. I think there is quad tree, octree, and all that. Okay, and these are very good for searching algorithm because lesser number of nodes are there, and also this create a data structure. So if you don't understand, just hear the terms. When you go deep into the subject, you will know. So it will create a data structure which is which creates a quicker way of finding the path. Okay. Uh, or the nearest neighbor or something like that. So just hear these terms. These are all available in this book. Okay, this may not be the part of the course, but which is you can read quadri, octree, and all. Okay, and learn more about approximate cell decomposition. But I think the cell decomposition, which we have already discussed, that is covered in the course. Um, okay, so let's do this exercise. Let's go and search for approximate cell decomposition. And yeah, so you can see here in this image, this is what I'm seeing, saying, yeah, the chord tree and these algorithms. So here you can see that near the obstacle, the grid is finer, and away from the obstacle, the grid is bigger. So the number of cells, will depend on, doesn't have to be constant everywhere. The number of cells doesn't have to be, blindly, okay, we divide the entire space into these many number of cells, okay, 1,000 cells. Instead, you put only 10 cell, like 100 cells in free space and have like more cells near the obstacle. So that is the idea of approximate cell decomposition. Okay, so this is like proper cell decomposition and this is approximate cell decomposition. Okay, so this is in 3 dimension also you can see we can do this. My screen is visible, right? Uh, wait. Are you able to see this diagram, right? 3D cell decomposition. Anyone? Are you able to see the cube? Yeah, you are able to see. Yeah. So this is not in the course, but this is something I am telling extra. Okay, so this topic is very interesting. Okay, so we will not go deep into these algorithms right now. Uh, okay, so but you can do this even in 3D. Okay, and also uh, one more thing I can tell is like we don't have to give like occupied and not occupied, right? So there is like we give 1 and 0. So we can also give probabilities. So depending on our sensor model, so whether what is the variance of the sensor, how accurate our sensor is, or how confident our sensor is that whether that particular grid has the obstacle. So let's say the sensor is only 60% confident. Okay, so this cell can have the value of 0.6, and this is definitely, then this can have 1. Okay, so like that also you can assign probabilities to the obstacles and all. So if you see the slam part, so this is where this is also important in the slam. Okay, the how you represent the map. Okay, so this is not just for path planning. Okay, so let's move on to the next question. Enough discussion for this question. If you have any doubt, you can ask. Voronoi diagram we have discussed. Okay, so which of the following comes under graph search algorithm? So this is very easy. So there is two things as I mentioned, search and construction. Okay, construction. Okay, so without pen it's more difficult to write. Okay, construction. So depth first is the search algorithm. Breadth first is the search algorithm. Cell decomposition, visibility graph, and Voronoi diagram are the graph construction algorithm which we have seen in the last question. Okay, so what is depth first? So suppose we have a graph like this, and okay, and then what we do is we will search. Okay, let's create more denser graph. Okay, now we have two options, right? We can either we start our search here from here, and we have two options. We go here, and then we look for here how much distance we have traveled, and then we come here and we see what is happening. Okay, or we go here, we keep on going inside till the end, okay, to see whether we are finding the goal, or we say that no, I will just first cover. So this is depth wise, like we consider one possibility and then we calculate further deep into that possibility, and then again one more step ahead till the end. and then we come back to the starting node, and then we find the second node, and then we again go into depth. So that is depth first. Okay. In breadth first, what we say is that we consider this possibility and this possibility. Both possibilities we will consider like parallelly. First we do this, then we do this. Okay. Now we say that this is better, then we do this, then we do this. Okay. So we always move like cover all the possibilities. So we move horizontally like this. In depth first we will move like deep inside. Okay. So that is the difference. Okay. So the heuristic cost for all nodes in Dijkstra algorithm. So okay, so what is heuristic? Okay, suppose this is the total cost. Okay, this is the cost of node plus. So what was the symbol used? Okay, I think it's g of n plus h of n is equal to c of n. Okay, so g of n is nothing but the cost uh, you have already traveled. Okay, the traveled cost. Okay, that to reach the node. Okay, and heuristic is nothing but your guess. Okay, your guess that how far the goal might be. The goal might be. Okay, so this is what how humans think, right? So suppose you are going to you went to some relative's house, and from there you want to go to the railway station. Okay, and the relative tells that okay, you can walk up to the railway station, and it is to the west of the house. Okay, now you don't know the exact path, but you know approximate. Okay, this is the direction. It's towards the west. So whatever is whatever paths you find while walking, you see a left turn, right turn, straight, and all. Whenever you reach a particular point and you see some options, you are more likely to say that a particular option which takes you in the west direction is more suitable, right? So you will have a higher, even though you don't know exactly. It can be possible that you walk on that path. It takes you to the west, but then there is a big, wall, and there is no way to go further. Okay, but still you, because you don't have any knowledge about either of the paths, you will say that okay, this path takes me to the west, so this path might have better chance for me to take me to the goal. Okay, so then this h of n is that particular part, and g of n is what how much you have already traveled to reach the that particular node. Why this is important? This is important because you don't want to go back and then again start again, right? Because you have already traveled a certain distance. Now you want to make small improvements. If you go back, then actually traveling back distance is more. Okay, so g of n is the traveled distance, and h of n is the guess. Okay, some value that you assign to each of the nodes. So yeah, someone has a question, or it's fine your understanding. So in Dijkstra algorithm, there is no h of n. Okay, this is h of n is there in A star algorithm. Okay, in Dijkstra algorithm, there is only g of n. Okay, so if there is question, please unmute yourself and ask. We'll go to the next. Okay, so this is choose the true statements. Okay, the potential field method. Okay, let me see whether I have started the recording or not. Okay, I have started. Uh, okay. The potential field method treats the robot as a point under the influence of an artificial potential field. Okay, so let's first revise what is potential field method. Okay, can anyone tell what is potential field method? You have seen the lectures, right? Anyone? Are you seeing the lectures? You should know what is potential field method. Anyone can you recall? So there are some obstacles, and this is our start point of our robot, and let's say S, and this is the goal point. Okay, so it is a very wonderful method. What we say is that now our robot, let's say this is the robot. Okay, it starts here. We say that let's give positive charge, positive potential to the robot. Okay, and we give the same positive potential to the obstacles also. Okay, so if we give so positive is just like one example I am taking. Okay, but what the idea is we give the same potential to the robot and to the obstacles. So what will happen? The robot and obstacles will repel each other, right? And we want that, right? We want the obstacle and the robot to repel each other so that they don't collide. And we will say that uh, we will give attractive potential or negative potential to the goal so that the robot will be attracted towards the goal. Okay, so you will have some vector field which will take the robot from the start point to the goal point while it is avoiding the obstacles. Okay, now what? So this method is very good. It's just a reactive method, but there are some problems with this method. So one of the famous problem is that the robot can get stuck into a local minima. So for example, the obstacle is of this shape. Okay, it's a concave obstacle. Okay, and your robot is here, and this is the goal point. Now what will happen? This goal will attract the robot in this direction. So robot will try to move here, but then this obstacle will repel the robot in the ulta direction. Okay, so robot gets stuck here, right? So because it cannot go further and it cannot go back, the forces get cancelled, the attractive and repulsive force, and the robot gets stuck over there. So this is called a local minima problem. So there are ways of getting out of it. Out of this, there are methods, but then this is a very annoying problem when we implement this. But still, a lot of papers use this, and it is a very popular method and being implemented. Uh, and there are ways to come out of the local minima. Okay, one of the ways is the brush fire algorithm. Brush fire algorithm. So you can look for it. It's given beautifully in the associate book. So let's solve this question. Okay, what happened? Why the pen is not active? Okay. The potential field method treats robot as a point. Yes, it is point, and this is the artificial potential. So there is no actual potential field, right? There is no actual charge. It's an artificial charge that we assume for the sake of the algorithm. Okay. The goal acts as a repulsive force. Wrong. The goal acts as an attractive force. Yes. And the obstacle as repulsive. This is correct. Superposition of all forces applied to the robot. Yes, this is also true. So superposition means we add all the forces. Okay. Okay, so let's move to the next question. From the below list of the algorithms, which of them does not use the deterministic graph search method? Okay, so bug algorithm doesn't use, right? All other multi-bug algorithm, I don't know. This also should not be using it. So A star algorithm is a graph search algorithm. Dijkstra is a graph search algorithm, and Graphspire is also very similar to a graph search algorithm. So it's essentially a breadth first algorithm. Yes. Okay. So Let's revise what is bug algorithm. Uh, so when we say bug algorithm, why is it called bug algorithm? Anyone? Because the robot is as
It
dumb
is
as a yes. Yes, Prasha.
it is like a bug.
Yes, the robot is like a bug. So what do you mean by robot is like a bug? So what property of the bug the robot has? What property of the bug the robot has? Like why are we calling a bug? Why are we not calling it a donkey? Okay, so the robot actually cannot see very far. Whatever sensor the robot has, it has a very less visibility. Okay, so we can say that it has no visibility. When it goes and hits the obstacle, it will come to know that okay, there is obstacle. Okay, so that is why it is called bug algorithm. Okay, so that is the capability of robot. Now with this capability of robot, okay, that the robot is only hitting and then coming to know that there is obstacle. Can we find a path? So answer is yes. And the way to do it is by applying this bug algorithm. I will just quickly revise the bug algorithm. So suppose this is the obstacle, and here our robot is there, and here the goal is there. Okay. So what will happen first? You know where the goal is. The robot knows where the goal is, but it cannot see the obstacle. So what it should do? It should move in the direction of the goal. Okay. How do you find the direction of the goal? You take tan inverse of okay y goal minus your robot position y x goal minus robot position goal. Okay. So this will always give you the direction theta. Okay. So you look at the OHOZ book, you will get more details. So you move in this direction, okay. But when it moves, it hits the obstacle. Now once it hits the obstacle, it remembers where it hit the obstacle. Okay, it will remember the hit point, PH, hit point. Okay. Now what it will do? It will say that okay, I have hit the obstacle. So like suppose there is a very dark room and you hit a table or you hit a wall and you suddenly realize that there are lot of things can be there, and what you will do, you will try to touch the wall and move, right? You touch the wall and you try to move. So that is what the robot does. Robot will what it will do, it will move little bit along. So it will first hit, then it will try to rotate little bit and again try to move, then it will again hit the obstacle. Okay, then it will again rotate little bit, try to move. Again, you will see, okay, there is obstacle. So it keeps rotating till it sees that there is no obstacle in this direction. So it understands, okay, this direction there is no obstacle, so it moves. Now it could have been right or left. Okay, so you have to choose one. Either you can rotate to the left or you can rotate to right. Then you move. Okay, then again you keep on checking whether there is obstacle or not. But you move in a way that you don't move very far away also. Okay, like this. You always move tangential to the obstacle, and so that you can follow the wall of the obstacle, and you completely follow the wall, okay, and come back to this position because you have memorized the initial position. Okay, you complete. Now once you follow the wall completely, while following the wall you are also keeping a track that which point was closest to the goal. Okay, so you memorize that this is the closest point, CP. Okay, now what you do? You go back to the that point and then you move towards the goal. And that is how you reach the goal. So this is called bug one algorithm. Okay, so because you are blind, you have to do this a very longish path you have to find. Okay, so that is called bug algorithm. So here you see that there is no graph search done anywhere. No graph search. Okay, so this is the bug one algorithm. There is bug two algorithm, bug zero algorithm. Okay, you can read it up. Uh, let's move on to the next question. We choose the following. So here you can see this is the bug one algorithm which I just now discussed. Bug one algorithm. Okay. There is also bug two algorithm. Let's discuss bug two also. So before bug two, let's look at bug zero. Okay. So suppose this is the start point and this is the goal point. Okay. What we do is we move towards the goal point, and when we see the obstacle, we follow the obstacle, and as soon as we become free, we move towards the goal. Okay, so this is what bug zero. Now you might think that, oh wow, this is better. So why not, why to have this kind of bug one algorithm where you are encircling the entire obstacle? So there are failure cases for bug zero. Okay, so for example, there is something like this, and there is this goal point is here, the start point is here, and you move towards the goal, but then you okay. Let's make it like this. Okay, so you move, you follow the obstacle, you become free. Once you become free, you'll again go up and you get stuck, something like this. Okay, so there are failure cases, and that's why bug zero is not a complete algorithm. So this word called complete. So complete algorithm means that if there exists a path, your algorithm should be able to find it. If it doesn't exist, then okay, it's fine. Okay, so it's bug zero is not a complete algorithm. Bug one is a complete algorithm, and bug two is also a complete algorithm. Okay, so in bug two, uh, I think the goal is here, the obstacle is here. What it will do is it will remember where it hit the obstacle. Uh, it will follow. Okay, so in this particular bug zero and bug one is giving the same. So let's see the failure case of bug zero. Okay, here. So what it will do is once you hit here, it follows. When it comes back to this path, okay, it remembers the starting point. So here actually it can actually follow like this and go. So this is also not a failure case. Okay, let me create a failure case. Uh, what will happen here? Hmm. Okay. Okay, let's see. Say that it's not possible at all to Yeah. So this is a failure case. Okay. Okay. So here is the start point, and the robot starts moving towards the goal. It hits. Okay. Now it, let's say, takes a left turn. It follows the obstacle. Okay. Now it becomes free. So it again comes back to this line. Then again it will go here and keep following. So it gets stuck in the loop. So what bug 2 says that you remember where you hit. Okay. So that you don't come back to this point, and if you are reaching there second time, you take another turn. So that is what bug 2 does. So you read the Hoy Choset book, that explains it much better. Okay, so now here the answer is bug 1. Okay, so this is the visibility graph method. So let's construct the visibility graph for this figure. Okay, so whatever is visible from the node you have to connect. So from 3 you connect 4, 8, 7 you connect 4, 9, 6, like this. Okay, so once you connect all these things, So you don't have to, create this mess, but that is how you connect. That's what I showed. Here you can see that, so when you connect the vertices 1 to 3, 3 to 8, and 8 to 2, and 3 to 6, and 6 to 2. Okay. So either this or this, one of them will be the closest path. So since no distances are given, we have to give the approximate answer. Okay. But the basically visibility graph means whatever vertex is visible, you connect that. Okay. So answer is 1362. Any doubt till now? If I am going fast, or if you want any specific algorithm to be discussed, can discuss that. Okay, so this is Dijkstra method. So in Dijkstra method, we have to find the answer here. So what was Dijkstra method? So Dijkstra method was that uh, you go. It's kind of greedy algorithm. So when we say greedy, it tries to choose a node that has the minimum cost. Okay, so for example, it will go to 10 first. Yeah, so let's go according to the algorithm. Okay, so because this is a big graph and it can be confusing. So I will just put it here. Okay. So the first step is that for every vertex in the graph dot vertices. So this is the graph, and for every vertex we first assign the value infinity. Okay, so we will assign infinity to all the vertices, right? And then what we'll do, and we will say we will have two lists. One is distance and another is previous. Okay, so we have two lists. Okay, and then what we do is distance. So the source distance we say is 0. Okay, and while q is not empty, okay, we add v to q. Okay, so every vertex will add to q. So let's have q over here. So q is a set of all the vertices. So there is s, there is 2, there is 6, there is 7, there is 5, there is 3, 4, and t. So t is the target, right? So q is the list over here, and we will say that okay, vertex in q with minimum distance u from the start point, okay, is chosen. So this is a greedy algorithm. So we choose the minimum distance wala node, and this is nothing but 2. So we choose it, and we remove 2 from the q. So let's remove q 2. Okay. Now what we say that for each neighbor v of u. What is u now? 2. Okay. So for each neighbor v of 2. So what are the neighbors of 2? 3. Only one neighbor, not s. S is also a neighbor, but we are seeing in the forward direction. So, okay, 3. We will do the dist of u plus the graph dot edges u comma v. Okay. So what will be that? Dist of u will be what? Dist of u is what? Anyone who will tell dist of 2? What is dist of 2? Infinity, right? Currently it is infinity, right? So infinity plus, oh, sorry. Okay. So initially we are choosing start node. Okay, start node. Okay, so currently it's S. Okay, so S node is the start node, and minimum of u will be what? 0. Its distance from itself is 0. So what are the neighboring node? 2, 6, and 7 are the neighboring node, right? So dist of u is what? 0. plus the graph dot edges. Okay, someone wants to join. Okay, Anthony has joined. Yeah. So list of start node is 0 plus graph dot edges of u comma v. So distance between start node and v. So let's choose v as 2. Okay. So it is 10. So alt is what? 10. Okay. So now dist of v was infinity. Is 10 less than infinity? Yes. So we update the dist of v. So let's have this dist column over here. Okay. Node. So this is a node. This is S and 2 and 6 and 7 and 5 and 4 and 3 and T. Okay. So S list is 0. There is no previous. Okay. Currently all the previous are undefined and all the distances were infinity. Only two's distance we found as 10. Okay. Right, and we assign the dist of v, dist of 2 as 10 and previous of v is as u. So previous of v as 2 as 0 or s, sorry, s. Now we go to the 6 for each na, so after 2 will come 6. So for 6 again we will get 24 over here because it is less than infinity and previous will be s. Right, for 7 we will get 12 and previous will be s. Now we have to go back, so we have to erase this infinity and we have to write down the distances 10, 24 and 12. Okay. Now what we do, we will go here. So while q is not empty, only s has been removed, right? We will go for vertex in q with minimum distance of u. So what is the minimum distance here? 10, right? Now we remove 2. Okay. Remove u. So from q we remove 2. Then for each neighbor v of u means what? Each neighbor of 2. Still in q. Still in q. So s is also a neighbor of 2, but it is not in q. Okay, so we will not take s. Right? So each neighbor of v, that is each neighbor of u, that is each neighbor of 2, is only 3. So let's analyze for 3. So distance of u, what is dist of u? U is 10. So now this calculation of alt will be here. Let me write it. ALT. Okay. Okay. Dist of 2 is 10 plus the graph edges between 3 and this will be 24. Okay. So this is nothing but 34. So we will get 34. 34 is less. 34 is less than infinity. So we will replace infinity by 34 and we will assign the previous of 3 that was undefined earlier as 2. So let's do that. Let's call this as 34 and so where is 3? 3 is here. So this becomes 34 and the previous is 2. Right? Okay. So who will tell what is next step? What will be here now? Okay, so while q is not empty, u, the vertex in q with minimum distance of u. Now which one has the minimum distance? Which vertex has the minimum distance? Are you guys following? So this is a question that will come definitely. It's a very highly probable question that can come in the exam as well as in the quiz. So Please understand this. It's not that straightforward. It's very straightforward actually. So, but still, like it's good to solve once. So, anyone, I assume that is you are understanding. Okay. So let me go back to the slides. Okay. Please stop me anywhere. Okay. So now, among all this, the minimum distance is 12. Okay. So 0 and 10 we cannot take. It is less than 12. But why we cannot take? Because it is no more inside the queue. Right. So now the minimum, the one is 7. So let's remove the 7 from queue. Okay. And now what we do is, for each neighbor v of u, that is each neighbor of 7, what are the neighbors? 6, 5 and the target t. Okay. For each of them we have to do this calculation. Okay. So what we do is, let's choose 6 first. Okay. So for 6 we go for the, okay, so this is an incoming edge, right? So we cannot take 6. I think we have to take the outgoing edges. Yeah, we have to take the outgoing edges. Okay, so let's take 5 and t are the neighbors. Okay, so this is 13. Dist of u is 12 here. So this will become 12. Let's calculate the alt. So this time I'll go fast because we have already done this process for other nodes. So this is 12 plus 13, right? And so it will be what? 25, right? And so we can write here for 5 as 25, and the previous node is 7. Okay, then we go for the t. T is 44. So similarly, t will be 44 over here. Previous node is 7, right? Now we have finished this two for 7. Okay, now let's move on. For 5, we have to update the value as 34, 34, and here is 44, 40. Okay, because it is less than infinity, we can update. Okay, so now we go to 6, node 6, because that is the minimum, because 7 is also gone out of the list. So 6 is the minimum distance u. So for 6, what are the neighbors? 3, 5 and 7. Okay, so let's consider 7 first. We can also consider any of them, but we have to consider one of them. So okay, let's consider 7. So once we consider 7, so the distance is 5 and 24. So 5 plus 24, it will be 29. So for 7, uh, is 29, but then it is not less than the already existing distance, right? So it is not less than the distance of 7. So we will not take this, consider this path to reach 7. So this path is cancelled. Okay, and we will not update the previous node of the start node. So this path to reach 7 doesn't make any sense. Okay, so what we do, we move on to the next node, 5. So 5, again we say 24 plus 21, that is 35. Again 35 is greater than 34. So this path is also not considered in the calculations because this condition is not satisfied, right? And similarly, here also 24 plus 18. So that is 34 plus 8, 42, which is again this value is 34. So 42 is not less than 34. So it won't go to this. So no, none of this is getting updated. So definitely our robot is not going to visit 6. Okay. So 6 is also removed. We have analyzed 6. Now let's go for 5. 5 is the minimum now. 5 and 3, anyone we can choose. So let's go for 5. Okay, so once we go to the 5, we already have the value. So we have reached 5 in this way. Okay, so now if we are touching the target point, so it's 18, right? 18, 15, 2. So this is inward arrow, I think. So this is inward arrow. So we don't have to consider the node 3. So there are two neighbors, 4 and T, right? So for 4, let's calculate 34 plus 15. The value will be 49, right? And for T, 34 plus 18, value will be uh, 44 and okay, 42, right? So now 42 is less than 44. Okay, so we have to update this according to this particular condition. So we have to update 42, and the previous node is the better node is 5 instead of 7. So this is the key step. Okay. So now our path looks like this. So are we done? No, we are not done because there are, so we are done with 5. Okay, we can cancel out 5, but there are two more nodes remaining. And once you do the two more nodes, you will realize that there are no updates here. Okay, because this is actually the shorter path. Okay, so I hope you have understood. Okay, for computer it is very fast. For us it took a lot of calculation. So this is a very good algorithm. It gives you the optimal path. It will actually find the shortest path. The only problem here is that there are no heuristics. So there is only g of n, right? So this is g of n is not plus h of n is not there. Okay, so but you will get the same answer. Okay, the right answer. You always get the right answer. So the answer here is, as you can see, 5 7 S to 7, 7 to 5, and 5 to T. Okay. So which graph search algorithm is used in graph fire algorithm? So what is graph fire algorithm? Let's see the graph fire algorithm. So this is, let's say, the start point, and there is a grid. Okay, in the grid, let's assign value 1 to the like you can assign any value to the obstacle, and let's say this is the start node. So what we do is we will assign the neighboring nodes as 2, then further node as 3, then 4, like that. Okay, and so like grass fire, suppose this is a patch of land with grass. Okay, and you start a fire over here. So how it will spread? It will spread evenly in all directions, right? So S2 2 2 3 3 3, and so basically the fire has reached 4, all the 4s at the same time. 4s, all the 5s at the same time. Okay, so it is, that's why the name is grass fire. Okay, so like that you will expand, and you will expand until you reach the goal. Once you reach the goal, you stop. Okay, so that is how the grass fire works. And so if you carefully look, it is a breadth first search, right? So you search along the breadth. Okay, so this is the breadth first search. Okay, so let's move on to the last question of today. Dash algorithm expands the node starting from the start with from the start similar to, okay, there is some grammatical error, so the sentence is not very coherent, but what it tries to say is that Algorithm expand nodes starting from the start, similar to the breadth first search. Okay, sorry, there is no grammatical mistake. I was not reading it properly. So, except that the neighbors of the expanded node are placed in heap and reordered according to their value, which corresponds to the cost. Subsequently, the cheapest state on the heap, the top element after reordering, is extracted and expanded. This process continues until the goal node is expanded, or no more nodes remain on the heap. A solution can be backtracked from the goal to the start. Okay. What is this? Start from the start, similar to the breadth-first search, except that the neighbors of the expanded nodes are placed in the heap to their value. Okay, so this is the keyword. Cheapest state on the heap. Okay, is extracted. So if you see carefully here, okay, what we are doing? We are saying that minimum distance u. So this is the cheapest state, right? Cheapest minimum distance. Or we say that the greedy. We choose a node which we don't know in long term whether that will be the best node, but for now we chose 10, right? Instead of 24 and 12. Okay. The 10 did was this node didn't come also in the answer. So we always go for the greedy one in Dijkstra algorithm. So that is what it says. It is similar to breadth first, but we are choosing the cheapest. So this is Dijkstra. Okay, so that is all. So all questions from the previous year assignment we have done. Uh, do you have any questions from your side? Then please let me know. I'll wait for some time for your questions. Or do you want to ask anything about any specific algorithm about path planning? Praharsha, Praveen, cute baby. Potential field path planning. Yes. Do you want me to explain the algorithm again, or you have any question?
No questions.
No question. Praharsha has no questions. Okay, you want again. So okay, so let's do it again. Okay. Oh, the AC is very cold. I'll just switch off the AC. Okay, the remote is not here. So okay, let's do this. Okay. So what we do is, let's say this is the start point of the robot and this is the goal point of the robot. Okay. And here some obstacle is there. Okay. What we do is, to the robot current position, we'll assign a potential, okay, a positive potential, okay, and we'll assign the same potential or the like positive potential. Okay, Akash has joined, but Akash, we have finished all the 10 questions. Uh, if you want, I will do a quick revision of all the 10, but okay, let's finish cute baby's question first. Okay, so we assign the same charge to the obstacles. So when the robot moves, so this is the like virtual charge. Okay, so when the robot moves towards the obstacle, it feels a repelling force. Okay, and the goal has a negative potential. Let's say. So what will happen? The robot will move towards the goal, will get attracted towards the goal, so it will start moving towards the goal. But when it comes near the obstacle, it will get a force. So basically, what happens? This is a robot, right? We calculate two forces. Okay, one force will be F obstacle, and one force will be F goal. So this will be an attractive force, and this will be a repulsive force. Okay, so and robot will move in a direction of the resultant force. Okay, this is equal to F R, or this is equal to R, resultant force. Okay, so how we define F obstacle? F obstacle we can define in a such a way that, okay, so this is not very exact, but what I'm trying to say is that when the distance between the robot and obstacle is less, you get more force, more positive force. Okay, so we will kind of say that, okay, it is inversely proportional to the distance of robot to obstacle. Okay, and the attractive force of the goal will be F goal will be negative the distance between goal and the robot, because when the robot is far away from the goal, it should be attracted more fast. Okay, so this is directly proportional with the F goal. Now when we add these two, what happens? We get a resultant force of the robot in some direction. So let's say robot is here, the goal is attracting this direction, and this obstacle is applying force this direction. We add these two force by vector addition, and we get some force in this direction. So robot, if it is robot is here, robot will move in this direction. Now you got cube way below, or you want some more detailed explanation? I don't know what exactly, but if you have any exact doubt, you can ask. Yeah. Okay. So who joined now? Akash Yadav joined now. Okay. So let me just quickly in 5 minutes I will just revise all the questions uh, for your benefit. Okay. So this is the first question, and we were asked which particular method is uh, dis- described by this statement. So it was saying that the edges are joined, which can see each other. So this is done in the visibility graph, and I also explained what are the different methods given in the option, right? Uh, Voronoi diagram method was one where we are, creating graphs which are equidistant from the obstacle. Okay, so we get very safe paths in Voronoi cell decomposition. We equally divide the space, uh, and in approximate cell decomposition, what we do is that we divide the space in a way that there is a coarser map in the free space and finer map near the obstacle. Um, but the answer for this question was visibility graph method. And here you see that which is a graph search algorithm. So depth first and breadth first are the graph search algorithm, and we discuss that how in depth first we try to analyze among the different possibilities. We pick one possibility and we go completely into the depth till we reach the goal, and then we go back and analyze the other possibilities. Whereas in breadth first we don't go very deep, but we analyze all the possibilities first, then we go one step ahead and then again analyze all the possibilities first, and that way. Okay, in question 3 we talked about what is heuristic, what it does mean by heuristic. So it's about guess that how far the goal might be, and it is our choice whatever value for heuristic we can give. And g of n is nothing but uh, the cost that we have traveled so far So for h of n will be 0 for Dijkstra's algorithm. Okay. Uh, then this was the potential field that we just discussed. Okay. Now this is the bug algorithms that we discussed. Bug 1, bug 2, bug 0. And so it's the bug algorithm is not a deterministic graph search algorithm. Okay, and we also discussed that bug algorithms are useful when the robot doesn't have any visibility, right? And okay, so this is also the question related to bug algorithm. Then this was related to the uh, visibility graph search, right? And we created a visibility graph like partially, uh, but we are supposed to join all the nodes. Okay, and then we say that okay, among the options, this is the shortest one. Uh, then we analyze this particular graph in detail using Dijkstra method, and we found the solution as S75T. So we followed this algorithm. What we do is for initially for every vertex in the graph, we will define the distance or the cost as infinity, and the previous node of that particular vertex we will assign as a different. Then we create the two lists, dist and previous, distance and previous, and we make, and it is labeled by all the nodes. Okay, and we create a list of q or a set of q with all the nodes. Okay, well then what we do is that for till q is not empty, till we have not analyzed all the nodes. Okay, what we will do, we will choose a vertex in q that has the minimum dist value. Okay, so the minimum dist value is for s, because s, because start node or the source node we had defined as 0 and others are infinity. So we start with s obviously because that is the minimum dist value, and then we see for each neighbor of s or each neighbor of u, okay, that is still in q, that has not been analyzed before. Okay, what is the value, the alt value. Okay, so the alt value is the new distance that is computed, so dist of u plus the edge. Okay, so for example for 2 it will be 0 plus 10. Okay, and then we see that whether the 10 is less than the already placed value infinity. Yes, it is less than infinity, so we update in this list, and we update the previous node of the no u here in this list. Okay, then we, once we do this, you will see sometimes the node will get replaced and sometimes it won't be replaced. Okay, then finally we will see what is the previous neighbor of the target, and then what is the previous neighbor of that previous neighbor, and then finally which one takes us to the start. Okay, the source. So that is how the Dijkstra algorithm goes. So if you have missed it, you can once it is posted on my channel. So let me show you my channel. Okay. So we just search for Suraj Borate. So there are a lot of Suraj Borates over here. So Suraj Borate 20310037. So this is my channel. You can go to the channel and you can see all our lectures over here, right? And alternatively on NPTL also. So there here you have the problem solving session. You click the problem solving session, click here, and you will see the problem solving sessions videos by me and the other TA. Okay, and the slides are uploaded in this presentation folder. Okay, so okay, let's see, revise the other question. Okay, so this was the breakfast. So brush fire algorithm is a breakfast question, and this was the last question where you were present. Okay. Okay. So anything that you want to ask, please ask. Anything regarding path planning or anything regarding mobile robotics course or robotics in general. So the battery of the laptop is down. So let me just put charger. Please unmute yourself and ask if you have doubts. We'll continue for some time. If you have no doubts, then we can stop the session. Okay, so nobody's asking anything, so I will assume that all good and see you in the next session next Friday. Uh, till then, bye. Uh, thank you for coming.